My name is Vinitha Ranganeni, and I'll be presenting Exploring Levels of Control for a Navigation Assistant for Blind Travelers. This is work done at Microsoft Research in collaboration with Mike Sinclair, Eyal Ofeik, Amos Miller, John Campbell, Andrei Kolobov, and Ed Kutrell. According to the National Federation of the Blind, in 2016, approximately 7 million people in the U.S. reported being blind or having low vision. The two most commonly used mobility aids by blind and low vision people are the white cane and guide dog. However, it can take a very long time to master using a white cane, and it can take up to 6 months to start working with a new guide dog, and their working life is typically 6 to 7 years. As a result, only 2 to 8% of blind and low vision people use a white cane, and approximately only 2% of the remaining individuals use a guide dog. Several applications and devices have been proposed to assist blind and low vision people. However, mobile applications do not provide enough information for local decision making. Some of these devices have been reported to be too heavy and bulky. Some of these devices provide the user control or the robot control, but do not provide a mixed control scheme. We propose Glide, a new mobility aid that provides local obstacle avoidance, is lightweight and portable, and provides a mixed control scheme. Glide weighs approximately 3 pounds. Its weight is offloaded on the base, which is roughly 9 by 9 inches. Glide has a pole connected to a small platform that rolls on the floor with unpowered wheels, requiring the user to push it ahead of them. This allows the user to control their speed and stop if they feel unsafe or need to readjust. There are servos for steering and braking Glide's wheels. Additionally, Glide's handle has haptic actuators that allows it to provide feedback to the user and a torque sensor for understanding directional input from the user. Glide's handle has 6 vibrotactile actuators. When the user twists the handle to the right 3 actuators will vibrate, acknowledging the user input. Similarly, when the user twists the handle to the left 3 haptic actuators will vibrate. When Glide wants the user to slow down, all 6 actuators will vibrate. Glide uses ROS2, and we specifically use NAV2 within ROS2 for navigation. Glide computes odometry by fusing sensor data from the wheel encoders and IMU and RGBD data from the RealSense camera. It uses the AMCL package for localization and regulated peer pursuit planner for local planning. We rely on pre-rendered floor plan of our building as a global map and generated global plans offline. In this work, we explored modes on a spectrum of control. On one end of the spectrum, the user has full control, and on the other end, the user is using a fully autonomous robot and can only input their destination. The first mode that we propose is the glide-directed mode. In this mode, the user sets their destination and controls their speed, while the robot steers, brakes, and navigates them to their destination. The user begins by telling the experimenter where they would like to go. In this example, the user says that they would like to go to the lounge. As the user begins walking, Glide will steer them to their destination while avoiding obstacles. In the future, we would like the user to be able to communicate their destination directly with Glide instead of an experimenter. The second mode that we propose is the user-directed mode. This mode is different in that it allows the user to select their desired direction of travel in addition to controlling their speed and selecting their destination. We tested this mode in an indoor hallway environment. The user can twist the handle to indicate their desired direction of travel. After they twist the handle, Glide will provide haptic feedback indicating to the user that they can begin walking. The user does not need to provide explicit input for walking straight. If the user twists the handle in an invalid direction, the brakes will engage. They will disengage after a few seconds if going straight is a valid option. If the user is at a T-junction where going straight is not an option, the brakes are engaged until the user inputs their desired direction of travel. If there is only one valid direction, Glide will not stop and will continue to steer the user in that direction. We verbally inform the users of directions available when they reach a junction. Glide brakes at every junction and waits for the user to input their desired direction of travel and then guides them in that direction. In this example, the experimenter tells the user that they can go right to go to the kitchen or straight to go to the lounge. The user twists the handle to the right and Glide guides them in that direction and brakes at the next junction. The experimenter then tells the user that they can turn left to go to the lounge or right to go to the kitchen. The user twists the handle to the left and Glide guides them in that direction and brakes when they reach the lounge. We ran a user study with 9 blind participants. We began by introducing Glide and having the participant try the Glide-directed mode 3 times and fill out a questionnaire about their experience. Then the participant tried the user-directed mode 3 times, filled out a questionnaire about their experience, and concluded with an exit questionnaire. For every trial, we recorded the time taken and the number of errors caused by incorrect alignment with Glide. We did not counterbalance the modes because our goal was not to compare the 2 modes, but to do a general analysis about each individual mode. The correct way to hold Glide is directly centered in front of you. An error is when the user deviates from that position by rotating their body, rotating Glide, or holding Glide out to their side. For the Glide-directed mode, we had 1 course with 4 turns that the users completed. For the user-directed mode, we had 4 routes that the user could choose from, 1 to the kitchen, 1 to the lounge, and 2 to the work area. We had 4 main questions we wanted to answer. Did users trust Glide? Were users confident when using Glide? Was Glide easy to use? And did users' performance increase over time? To answer these questions, we asked participants to state their agreement with the series of statements on a Likert scale. About 70% of participants trusted Glide in the Glide-directed mode, and about 60% of participants trusted Glide in the user-directed mode. About 70% of participants agreed that Glide inspired confidence when they were walking in the Glide-directed mode, and a little bit more than 75% agreed in the user-directed mode. 100% of participants agreed that Glide was easy to use in the Glide-directed mode, and 95% agreed in the user-directed mode. The time taken in the Glide-directed mode decreased as users continue to use Glide. We cannot say anything about the user-directed mode because the routes taken and the lengths of the routes varied. The number of errors across all modes and trials decreased. To summarize, users trusted Glide, users were confident when using Glide, users found Glide easy to use, and their performance increased over time. While Glide has shown much potential, there are several areas for improvement. First, we'd like Glide to be able to accommodate faster walking speeds. Next, participants found it difficult to stay directly behind Glide. Glide needs to be able to handle various positions of users with respect to it. Currently, Glide relies on a global map. In future iterations, we would like Glide to be able to map and navigate at the same time. Finally, Glide can currently only operate in single indoor floor plans. We would like Glide to be able to operate in more complex environments with overhangs, stairs, elevators, and ramps. Thank you for your time, and I'm happy to answer any questions.